A telescope switched on in Chile, pointed itself at the sky for about 10 hours, and in that single short window found more previously unknown asteroids than most professional observatories find in years. Then it kept going. Stick around, because I'm about to walk you through exactly what the Vera C Rubin Observatory captured the moment it opened its eyes, what it has found since, and why astronomers are calling this the single biggest leap in how we watch the sky in an entire generation. And hit subscribe now, because this channel breaks down real published research without the exaggeration, and you do not want to miss where this story is heading next. Before we get into what this telescope actually found, it's worth being upfront about the timeline, because a story like this deserves accuracy over urgency. The images that first stopped astronomers in their tracks were unveiled at a public event in Washington, D.C. was in June of 2025. That was the moment the world first saw what this machine was capable of. But this is not simply old news. Because in the time since that first reveal, the observatory has kept running, kept scanning, and kept adding to a running tally of discoveries that continues to grow substantially even now, with a major new batch of results confirmed as recently as this spring. This is very much a story still unfolding in real time, and the first images were only the opening chapter. To understand why this particular telescope generated this much excitement, you first have to understand who it's named after and what it was actually built to do. Vera Rubin was an American astronomer working through the 1960s and 70s who noticed something deeply strange while studying the rotation of spiral galaxies. Stars on the outer edges of these galaxies were orbiting far faster than the visible matter within them should have allowed, based on ordinary gravity and the amount of stars and gas astronomers could actually see. Rubin's careful. Repeated measurements became some of the strongest evidence ever gathered for the existence of dark matter, an invisible form of matter that neither emits nor reflects light, but which appears to make up the vast majority of the matter in the entire universe. She spent decades of her career building the exact kind of rigorous, repeatable observational evidence that could stand up to scrutiny. And decades later, the observatory bearing her name was built with a very similar philosophy in mind: watch, measure, and repeat, over and over, until the picture becomes undeniable. The observatory itself sits atop Cerro Pachon, a mountain in Chile chosen for its high altitude, dry air, and exceptionally clear dark skies, a location shared with several other major astronomical facilities. At its heart is the Simone Survey Telescope, paired with something called the LSST camera, built at the CEL-AC National Accelerator Laboratory. According to NSF and DOE officials, this camera is the largest digital camera ever constructed for astronomy, capturing images at a staggering 3,200 megapixels per exposure, roughly the resolution equivalent of hundreds of ordinary smartphone cameras combined into a single sensor, mounted on a telescope engineered to move quickly and precisely enough to photograph the entire visible night sky, over and over every single night, for the next 10 years. That last detail is the part that genuinely separates this project from almost every other major telescope that came before it. Facilities like the James Webb Space Telescope are built to stare intensely at one tiny patch of sky at a time, gathering extraordinarily detailed information about a single distant object. Rubin was built to do almost the opposite. Its mission, called the Legacy Survey of Space and Time, involves repeatedly photographing the entire available sky in extraordinary detail, night after night, for a full decade, creating what officials have described as an ultra-wide, ultra-high-definition time-lapse recording of the universe itself. Rather than a handful of detailed snapshots, Rubin is designed to produce a genuine, continuously updating movie of the sky, capable of catching anything that moves, flickers, explodes, or changes, almost anywhere in view, almost as soon as it happens. If you're the kind of person who wants stories explained clearly instead of buried under jargon, go ahead and drop a like on this video right now, because it genuinely helps this kind of content reach more people who would enjoy it. On June 23rd of 2025, that project produced its very first public results, and the reveal event in Washington, D.C. was treated less like a routine science briefing and more like the unveiling of a genuinely historic achievement. The first image shown to the public displayed a section of the Virgo cluster, a dense gathering of galaxies, showing two prominent spiral galaxies, 3 galaxies caught mid-merger, entire additional galaxy groups both near and distant, and countless individual stars from within our own Milky Way, all captured with striking clarity. And according to the observatory's own statement, that stunning image represented only about 2% of the observatory's full field of view in a single exposure, a small preview slice pulled from an image far too enormous to display in full at any normal resolution. A second image released that same day showed the Trifid and Lagoon nebulae, 2 enormous glowing clouds of gas and dust sitting several thousand light years from Earth, popular targets for amateur astronomers on any clear summer night. Rubin's version, though, was built by combining 678 separate individual exposures, gathered across just over 7 hours of observing time. layering them together to reveal faint structural details in the gas and dust that would be completely invisible in any single shorter exposure. According to the observatory, that one combined image alone was built from approximately 2 trillion pixels of data. Here's the detail that tends to stop people in their tracks once they hear it laid out plainly. All of this, the Virgo cluster image, the nebula composite, and everything else shown that day came from just over 10 total hours of test observations gathered before the telescope had even begun its actual 10-year survey mission. According to figures released by the observatory team, in that brief test window alone, Rubin had already captured images containing millions of galaxies and Milky Way stars, alongside thousands of individual asteroids scattered throughout our own solar system. That last part, the asteroids, turned out to be the single most talked about result to come out of the entire first look announcement. According to NOIRLab, the organization managing the observatory's operations, in roughly 10 hours of observations, Rubin identified 2,104 asteroids in our own solar system that had never been recorded by any telescope before, including 7 near-Earth asteroids, none of which pose any danger to our planet. To put that number in perspective, officials noted that all other ground and space-based observatories around the world combined typically discover roughly 20,000 new asteroids in an entire year. Rubin had matched more than a tenth of that global annual total in a single overnight test run. Jelko Ivezic, deputy director of Rubin's survey project, made the comparison even more striking in comments given at the reveal event, noting that this single batch of discoveries was roughly 5 times larger than the combined total number of asteroids discovered by every astronomer on Earth, across the 2 full centuries since the very first asteroid was ever identified. According to Ivezic, Rubin is now positioned to outdo 200 years of cumulative human effort in this specific area within just a couple of years of full operation. If you have found this as fascinating as I did while researching it, drop a comment letting me know, because it genuinely helps me figure out what other space stories are worth covering next. And this is exactly where the story stops being something that happened once, back in June of 2025, and becomes something still actively unfolding today. As Rubin's actual 10-year survey mission got fully underway, the discoveries kept compounding. According to a NOIRLab announcement from earlier this year, early survey data released beyond that original first look batch pushed the observatory's running total of newly discovered asteroids past 11,000, a substantial jump from the original 2,104 announced at the initial reveal. That same report noted that roughly 600 of the objects originally counted among the first batch of discoveries have since been formally connected to earlier historical observations by the International Astronomical Union's Minor Planet Center, and reclassified as recovered objects rather than brand new discoveries, a normal part of the ongoing verification process as more data comes in and overlaps with older, less complete historical records. According to reporting on this more recent batch of results, the newly confirmed asteroid count includes additional near-Earth objects, directly relevant to planetary defense efforts here on Earth. Researchers have estimated that once Rubin is fully operational across its complete 10-year survey, it could increase the total known share of larger, potentially hazardous near-Earth objects from roughly 40% of the estimated total population up to as much as 70%, simply through consistent, repeated monitoring of the entire visible sky. Scientists studying planetary defense have long pointed out that the greatest risk from a hazardous asteroid impact often comes not from the objects we already know about, which can be tracked and modeled well in advance, but from the ones we haven't found yet. Rubin represents, according to researchers involved in the project, one of the most significant single advances in closing that exact gap in modern history. Asteroids are far from the only thing this telescope is built to catch, either. Because Rubin repeatedly scans the same regions of sky over and over, comparing each new image against everything captured before it, the system is designed to automatically flag anything that changes, brightens, dims, or moves between observations, and to issue an alert about it, in some cases within roughly a minute of the data being captured. According to project officials, this capability is expected to make Rubin extraordinarily effective at catching entirely new categories of short-lived cosmic events, distant supernovae exploding in real time, pulsating variable stars, changing brightness and predictable rhythms, and rare high-speed visitors from beyond our own solar system entirely. That last category deserves its own moment of attention because it touches on one of the more genuinely exciting open questions in modern astronomy. So far, in all of recorded history, astronomers have only ever identified 2 confirmed interstellar objects, meaning objects that formed around a different star entirely and simply happened to pass through our solar system on their way through the galaxy. 1I, Oumuamua, discovered in 2017, and comet 2I, Borisov, discovered in 2019. Both were spotted only after they had already entered our solar system, leaving astronomers relatively little advance warning and limited time to study them closely before they moved on. According to officials at the observatory, Rubin's combination of an extremely wide field of view and its ability to scan the entire sky repeatedly is expected to make it the single most effective tool ever built for spotting these rare interstellar visitors, potentially catching future examples earlier and in far greater numbers than has ever been possible before. Picture, for a moment, exactly what a single working night at this observatory actually looks like, because the scale of it is almost difficult to hold in your head all at once. The LSST camera, roughly the size of a small car, sits mounted on a telescope engineered to swing rapidly between different patches of sky, capturing a new, enormous exposure every few seconds, then instantly moving on to the next patch, systematically tiling its way across the entire visible dome of night sky above Cerro Pachon, over and over all night long, every clear night, for 10 straight years. According to officials involved with the project, the sheer amount of data gathered by Rubin in just its first single year of full operation is expected to exceed the combined total data output of every other optical observatory in history. Combined, sitting somewhere in that endless, nightly flood of data, are objects nobody has ever seen before. Asteroids, comets, dying stars, and possibly, if researchers studying the outer solar system are right, even a long hypothesized, still undiscovered planet, quietly waiting to finally be caught on camera for the first time. That last possibility is worth being specific about, because it connects directly to one of the biggest open questions in planetary science today. For years, astronomers studying unusual clustered orbital patterns among distant objects at the edge of our solar system have argued that the evidence points toward a large, undiscovered planet, sometimes called Planet 9, hiding somewhere in the outer solar system, never yet directly observed. According to researchers involved in that hypothesis, Rubin represents one of the best realistic opportunities yet to finally settle that question directly, either by capturing the predicted planet itself moving slowly across repeated images over time, or by gathering enough additional data on distant objects to meaningfully strengthen or weaken the existing case for its existence. It is worth being clear that this remains a genuinely open question, not a settled prediction, and Rubin's survey is still in its comparatively early stages. But it stands as one of the clearest, most concrete examples of exactly why a telescope built to patiently and repeatedly scan the entire sky, rather than stare intensely at one small patch of it, might finally be the tool capable of resolving a mystery that has quietly persisted for more than a decade. It's worth being honest, too, about the scale of what's still ahead, because the first look results, as remarkable as they were, genuinely represent only the very beginning of this project. The full 10-year legacy survey of space and time is still in its early stages, meaning the asteroid counts, transient alerts, and galaxy catalogs described in this video are almost certainly a small fraction of what the observatory will eventually produce by the time its mission concludes. Researchers across dozens of institutions worldwide are still in the process of building the analysis tools needed to make full use of the sheer volume of data Rubin is generating, meaning some of the most significant discoveries buried somewhere in that data may not even be identified by researchers for months or years after the observations themselves were originally captured. So, what does all of this actually add up to? A telescope named after a scientist who spent her career proving that the universe contains far more than what we can directly see, switched on for the first time, and in barely 10 hours of testing, before its real mission had even officially begun, it had already matched a meaningful fraction of an entire year's worth of global asteroid discoveries, revealed nebulae in detail never captured before, and photographed millions of galaxies in a single sitting. In the time since that first reveal, it has kept going, pushing its asteroid count past 11,000 and counting, with a full decade of continuous nightly sky scanning still ahead of it. Whatever else this observatory eventually finds, hazardous asteroids caught early enough to matter, a long hypothesized ninth planet finally confirmed, or something entirely unexpected that no one has predicted at all, the first images alone made one thing clear. This is not simply another telescope. It is closer to a continuously running record of the entire visible sky, and it has already found, in less than half a day of testing, more than most observatories manage to find in years. If stories like this one, grounded in real published research rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because Rubin is only just getting started on its 10-year mission, and there's a real chance the next update on this observatory is even bigger than the last one. Thanks for watching, and I will see you in the next one.